We're back to fight the evil. In this video, we're going to talk about the logical AND operator, which is a logical operator that we can use to combine two propositions and test to see if both propositions are true simultaneously. Let's jump right into a formal definition. Here we see that the logical AND operator of propositions P and Q is denoted using P and Q. That symbol in between the two propositions P and Q is called an ampersand, and we read that notation P and Q. The proposition P and Q is true exactly when both P and Q are true. In other words, when we test to see if both propositions are true simultaneously, that test is true when both of those propositions are true underneath. We can take a look at a truth table associated with the proposition P and Q. Notice that there are two components of that proposition. We have the component on the left side of the ampersand symbol, and then the component on the right side of the ampersand symbol. Each of those components is a proposition in and of itself. In other words, each component can be either true or false. Well, we have two components of this proposition, each of which has two separate options, meaning that we have four total possibilities. We have the possibility that P is false and Q is false, or we have a possibility that P is false and Q is true. We also have a third proposition where P is true and Q is false. And then we have a fourth proposition where P is true and Q is true. What we're going to do with P and Q is test its truth value under all four conditions. Remember that P and Q is true exactly when both P and Q are true. So let's check the first one. When P is 0 and Q is 0, in other words, P is false and Q is false, those are both not true, so P and Q is also false. Similarly, when P is 0 and Q is 1, P false, Q true, both are not true, so P and Q is false. We go down to the third condition where P is 1 and Q is 0. In other words, P true, Q false. Both P and Q are not true. Thus, we label the combination under those conditions to be false also. In the fourth condition where both P is true and Q is true, by definition, that is exactly when P and Q is true. So if P is 1 and Q is 1, P and Q is also 1. In other words, we've tested that position to be true in that case. Notice that for the proposition P and Q, there is only one truth value out of all possible options, which happens when both P and Q are true together. That is exactly what this definition says. The proposition P and Q is true exactly when both P and Q individually are true. In our work together using MATLAB, we're going to use the ampersand symbol to do the logical AND operation. In other words, let's define something called an AND operator. The AND operator, denoted using the ampersand, remember that's this special symbol, which kind of looks like a squiggly AND. That symbol is used to perform AND operations in MATLAB. Let's test the AND operator in MATLAB by using logical scalars to evaluate a single row in our truth table. Specifically, we'll go ahead and set P equal to a true proposition. Notice that P gets set to logical 1, and we'll set Q equal to a false proposition, which gets logical 0. In this situation, we're down on the third row of this particular table. P is true and Q is false. We made a claim that if we now evaluate P and Q, notice that expression is a logical scalar because P is a logical scalar, Q is a logical scalar. We're claiming that the ampersand is the AND operator. We've said by this table that P and Q as a proposition should evaluate at false under these assumptions because both components are not true in this case. Let's go ahead and push enter. Notice that is exactly what MATLAB returns to us. P and Q is false because both components are not simultaneously true. Let's test the fourth row of this truth table using logical scalars. We'll set P to be true. That is a proposition stored as a logical scalar whose value is 1. We'll also set Q to be true as well. So now we have two propositions, both of which are true. The AND operator asks the question, are both of these true simultaneously? In this case, we produce logical one value, meaning this proposition is true because both components are evaluated to be true in the background. Notice in all three cases of P, Q, and P and Q, these are all stored as logical scalars, and indeed we can confirm that in the workspace. P is a one-by-one array stored using the logical data class. In other words, it's a logical scalar. Q is a one-by-one array stored in the logical data class, aka logical scalar, and the output of this test is also a one-by-one logical scalar. One interesting note here is we could have saved the output of this proposition using the AND condition, so P and Q. Let's call that a test, and we can say, please store the output of this test in a variable called test. Now when I push enter, we see that the test evaluates as true since both P and Q were true for this particular instance. Now, of course, in MATLAB, when we're using the logical data class to assign values to variables, we're not stuck with one-by-one dimensions. We can actually go in any dimensions. That's the whole point of MATLAB, matrix laboratory. This is an array-based language. We saw that previously. Specifically, we could create logical vectors. So in this case, let's actually recreate the entire truth table we see on screen using MATLAB variables. So we'll create a set of logical scalars stored in a column vector. So in this case, we see that the first column of this truth table has values 0, 0, 1, 1 stored in 4 separate rows. So that's 0, end of row 1, 0, end of row 2, 1, end of row 3, 1, end of row 4. Remember, however, what we want to do is not store these in the default double numeric data class, but instead store this as a logical vector, which means I need to actually store each of these as a logical scalar. That's exactly what the logical function is designed to do. So notice this is a 4-by-1 logical column vector whose first two values are 0 and second two values are 1. That's the exact first column of my truth table. Let's go ahead and create a second column vector, which we're going to use the same call. We'll start with a logical function, and then we'll go ahead and store this as 0, 1, 0, 1. That's the second column of this matrix that we see up here. Oh, I'm sorry, the second column of this truth table. When I push enter, notice this is a logical column vector with the same values as the column in Q. The third thing that we want to do is we want to combine those together. So notice if I were to do P and Q, MATLAB is actually going to look at P right next to Q and then do the AND operations within the individual entries of the left and right arguments to that operator. Notice that P and Q actually produces the third column of my truth table, which is exactly what I want. Moreover, we can go back to a previous video where we talked about the column partition of a matrix. In that video, we saw that we can create an entire matrix using column by column definitions. That was a part of a block partition definition of a matrix. To do that, we write the left square brace, the right square brace. Let's go back in. The first column we're going to define as P. Each column is demarked or delimited by a comma. So end the first column at P. Now we're going to take the second column at Q, push a comma, and then the last column of this thing is going to be P and Q. When we push enter, this output, which is a 4-by-3 logical matrix, or another way to say that is a 4-by-3 non-vector matrix of logical scalars, whose value matches identically the truth table for our P and Q proposition. The first two columns of that matrix represent all possible combinations of truth values for proposition P and Q. And the third column of that matrix shows the corresponding truth values for the proposition P and Q. Let's take a look at a fourth example where we take the logical AND operator between logical matrices, specifically non-vector matrices whose individual entries are logical scalars. In this case, we're going to create two matrices in memory. The first one is going to be matrix A. Notice matrix A is a 6-by-6 matrix. The first, third, and fifth rows are non-zero. Specifically, they are scalar multiples of the ones vector. So let's create A first. The first thing we're going to do is set A to be a 6-by-6 matrix of all zeros. Then what we're going to do is pick off the odd number rows, number 1, 3, and 5. Notice that the first row is 2 times all ones. The third row is 4 times all ones. Well, what size is the all ones? It's a 1 by 6. And then the fifth one is 8 times all ones. So specifically, I should probably have an all ones vector. Let's call that 1. And the size of that vector is going to be a 1 by 6. Then what we're going to do is say, I want to go to the odd rows. So I'm going to start at row 1, go up by 2, and go to 5. And I'd like to go in all columns. Now I want to fill that sub matrix with specific vectors. Which vectors do I want? Well, I want 2 times my 1 vector in the first row. Remember, I'm going to go down to the second row. The second row of this partition is going to go from 1 to 3. So this is going to be 4 times my 1 vector. And then the last row of this partition is going to be 8 times my 1 vector. When I push enter, notice my matrix A is the exact matrix that I wanted, which has all 2s in row 1, all 4s in row 3, and all 8s in row 5. All other entries of that matrix are 0. Let's go ahead and clear our command window and then store matrix B. Matrix B is a similarly structured matrix, but instead of having scalar multiples along the rows, it has scalar multiples along the columns. Also, instead of these being on only odd rows, here we have even columns. So in this situation, what we do is we initialize this, and we'll go ahead and call this all zeros. How many zeros is it? Well, it's a 6 by 6 matrix. And then what we're going to do is say, well, I know that I actually want to go all rows, and then I'm going to pick off special columns. Which column am I going to pick off? Well, I'm going to pick off columns 2, 4, 6. Remember, indeed, if I were to go ahead and just highlight those and push enter, MATLAB will actually just execute the code that I've highlighted. So in this case, the colon notation addressing says, please pick off columns 2, 4, and 6. What do I want those to be defined as? Well, I know that this is going to be looks like 16 is the first one, and I'm going to times that by the 1's vector. But remember, the 1 vector is a 1 by 6. In this case, I want the transpose of that vector. Also, remember, when I'm doing a column partition, I want to do so by delimiting the individual columns. So at the end of the first column, I'm going to go on to the second column. It's going to be 32 times 1, and I want to take the transpose of that. In this case, I'm going to go ahead and say I need to take the transpose inside. Looks like if I were to actually take the transpose inside, then multiplied by 16, I'd be in a better position. And then the last one looks like in row 6 of this matrix, I want to take 64 times. Now let's go ahead and open and close parentheses, and I'll take the transpose. Notice my matrix B is the exact matrix that I want. We've just finished our variable declarations for A and B. Notice A is a 6 by 6 matrix that is stored using the double variable class. In other words, this is a numeric matrix, each of whose entries is stored using the double class. B is a 6 by 6 matrix, each of whose entries is stored using the double class. Remember, this whole set of videos is about logical data, so we're going to create logical copies of both of those. In order to do that, we'll call the logical function. In this case, we'll say LA stores the logical version of A, which is going to give me a true when the values of A are numeric non-zeros that are definitely numbers. So when I push enter, notice I get logical ones, individual logical scalars, at every single entry where the corresponding values of A are non-zero. And I also get logical zeros at every entry where I have 0 A values. Similarly, I could say LB is equal to the logical of B, which is going to return the same type of result, 1 where I have non-zero values of B, and 0 where I have 0 values of B. Now let's go ahead and use the AND operator on LA and LB. Notice what MATLAB is going to do is actually take the AND operator on each individual entry pair. Over here on screen, we see kind of a visual representation of what we've done in MATLAB. Then when we take the AND between them, MATLAB is going to use this truth table to evaluate individual AND. So LA and LB in entry 1, 1, it's going to take entry 1 of LA and then logical AND it with entry 1 of LB. Well, 1 and 0 is 0 because that's what the truth table says. So the first entry of LA and LB should be 0. On the other hand, if I look in row 1 and go to column 2, when I take this operator and say LA and LB, MATLAB is going to take entry 1, 2 of LA, compare it with entry 1, 2 of LB. We notice that this 1, 2 is 1. 1, 2 in LB is 1, so 1 and 1 becomes 1 based on my truth table. MATLAB is going to do this 36 separate times and produce the corresponding matrix. Notice what we have here though, the row 1 is going to be true 1, 2, 3 places, since that's where row 1 and the columns are non-zero. Row 2 is going to be true exactly 0 times because all these are 0. Row 3 similarly is going to be true 1, 2, 3 times. So I would expect 1, 2, 3 times 3. So basically we're going to have 9 non-zero entries in positions 1, 2, 3, 2, and 5, 2. Also in positions 1, 4, 3, 4, 5, 4. And then finally in positions 1, 6, 3, 6, and 5, 6. Let's go ahead and push enter and see what we have there. Notice that's exactly what we get. In other words, the AND operator on the left-hand side and the right-hand side could be logical scalars. We could have logical vectors on both the left and the right-hand side, or logical matrices on the left and the right-hand side. In this introductory video, we're focusing on the situation where the input on the left has identical sizes to the input in the right. In a later video, we're going to see that that is not necessarily the case. We can do something called compatible sizes. We're not going to worry about that right now. We're going to focus on the easiest case where we use the logical AND operator and both inputs have identical sizes. To close the tutorial portion of this video out, I want to give a fun interpretation of what this LA and LB matrix represents. Remember that A had non-zero values in the odd number rows, and B had non-zero values in the even numbered rows. When I took LA and LB, what I was asking MATLAB is, what are the locations of shared non-zero values in both matrices A and B? And we notice those locations are exactly where these logical ones show up. I challenge you to come up with an interpretation if I were to take not LA, so here we'll go not LA, and LB, what does that mean? What do these positions represent? We could go further. What if we took LA and not LB? The moment I push enter on that, notice I get positions that are non-zero in A and 0 in B. And then finally, what if I wanted to find the not LA and not LB? Well, this would be positions in A that are 0, in other words, that are not non-zero. This is positions in B that are 0, in other words, not non-zero. When I look at not LA and not LB, I'm looking for where are the positions in both matrices that are 0. When I push enter in that, even rows of A and the odd columns of B, that's exactly the matrix that we see here. Do you notice something interesting about those 4 propositions, LA and LB, not LA and LB, LA and not LB, and then not LA and not LB? Each of those propositions has exactly 9 non-zero entries. There are 4 separate conditions. 4 times 9 is 36. In other words, if you were to look at these on the aggregate, you get all 36 entries. I'm going to let you think about that on your own. That concludes the tutorial portion and leads us into the community challenge of today. In the comments section below, please write your ideas about how you might apply the logical AND operator to solve problems in MATLAB. You can do this by actually listing your own code that you write as you become more sophisticated. You can also link to websites where people have good descriptions of this, or you can give examples of videos where people show you how they're using this. I'll give one major hint that if-else statements and branching statements in MATLAB are very powerful to be able to do different operations depending on which conditions are true and false. However, I know you all are super hardworking and creative. I look forward to reading and learning from your comments below. Of course, I'm always excited to get your questions and comments, and I look forward to seeing you in the next video.